So our reminder on page 41 from Phys Sci is that it will turn, an acid will turn litmus and universal indicator red. Acids will conduct an electrical current because for it to be an acid it needs to be in solution. It tastes sour, for example lemons, and so if you get some acid on your fingers it's quite tacky. And we know our reactions from Phys Sci. You are expected to have memorised / learnt these reactions. They were on the Phys Sci formula sheet. They are not on the chemistry formula sheet because you are very familiar with them. So you have to know that. And if we look at, like in the booklet, we've got hydrochloric acid reacting with sodium hydroxide, producing sodium chloride and water. Okay, so you need to be able to write any of these reactions. So it could be magnesium hydroxide, it could be nitric acid. It doesn't matter which acids and bases they are. You need to know that you're going to produce a salt and water. This is the full molecular, if you like, equation. Now we're in big school, we are expected to write ours as Ionic equations. So this is the preferred answer, or if you like, really it's the expected answer when you're being marked. The acid plus reactive metal. So without looking in your books, do you know what you make?
Salt plus hydrogen? Because it's sort of on the formula sheet in an incredibly roundabout way.
Is that?
It's on the formula sheet in an incredibly roundabout way. On the organic thing, it has the carboxylic acid reactions.
Yes.
Which are in the right order
That's
as
true.
that.
That's still an acid, so there's a clue there on there. So, yeah, good plan. It also has this in a roundabout way on there, doesn't it? Because it also has the neutralisation, doesn't it?
Yeah.
Okay, so if we have an acid, and our example in our booklets is sulfuric acid, and our reactive metal is zinc, but it doesn't matter what it is. It could be magnesium, calcium. We are going to produce the salt and hydrogen gas. Now, if I write this out as an Ionic equation, just a reminder that with the net ionic equation, you need to make sure that your charges are balanced on either side of the reaction arrow. So here we end up with no net charge for our reactants, and it's the same for our product. For this one, our net charge for the reactants is 2+, but that is the same as for our product, so our charges are balanced. The acid plus a hydrogen carbonate and the acid plus a carbonate. Again, these are reactions that we've done many times, so hopefully you are familiar with these. and that you know that you're going to produce a salt plus water plus carbon dioxide. Now, sometimes these cause some issues and people come up with some creative balancing, because we don't, you're probably more familiar with, say, the calcium carbonate, because we use that a lot, but it's the same reaction. And this time we've got hydrochloric acid again, and we've got sodium hydrogen carbonate. And it can be a solid or, in this case, it's aqueous, it's in solution. And that's basically it. It's very easy to balance. CO2 is coming from the carbonate part of the ion here. The other oxygen from the carbonate part is into the water. And we've got a hydrogen here and a hydrogen here. And then we've got sodium chloride. So if we look at what's happening with our reaction, we've got the hydrogen ion reacting with the hydrogen carbonate ion. And like I said, this is probably the one that causes the most confusion. It's on your table, the list of common ions, it's there. But some people just make stuff up. So if we take out our spectators, we've produced carbon dioxide and water. Okay, so that's just a reminder of the the reactions of acids that was on the fissile formula sheets. And it's also a reminder to make sure that you can write net ionic equations for your reactions. And if you find something that you're not familiar with in a question, then look it up on your formula sheet. See, it'll be there. Another reminder on this side is about strong acids and weak acids. Strong acids completely ionizing water. And now weak acids only partially ionizing water. And we are now quite familiar with what this means in terms of equilibrium reactions. So if I bubble hydrogen chloride gas in water, then basically I'll form hydrochloric acid, where the bulk of the ions, 99.99% whatever, are separated, completely ionized. So that's what that means. By saying completely ionized, I'm indicating it's a one-way arrow there, and it's not going to go back. For our partial ionization, the one we always love, and we should really react that with water. If I draw this out, it's this hydrogen ion, or the hydrogen in that position there, that can leave the molecule. It's the one attached to the oxygen. Which is why we write our FNO ion out like that, just to indicate that the H plus ion has come off here and we've left a negative charge then on the oxygen there. Now, I should really represent this like this, where it's only a very small amount that that actually ionizes. Most of it is still in this molecular form. Where it could be, I think it's around about 3% ionization, something like that, 2.5%. So that means about 97% of it's like this. That's why it's weak. Just as a reminder, if we're talking about concentration, then it can be concentrated or dilute. Okay, these are the terms for how much stuff is present. Whereas strong and weak, this is to do with ionizing. How ionized is it? If we turn over the page, we've got a little blurb there reminding us of the properties of bases, that they turn litmus and universal indicator blue. They will also conduct an electrical current because they also form ions in solution. These ones taste bitter. They can react with acids to produce a salt and water, which we've already looked at before. And they produce hydroxide ions. And so these are the metal hydroxide bases. And these are the group 1 and group 2 metals. Just a reminder from our periodic table. Group 1 here, they're called the alkaline metals. Okay, because they react with water and they'll form the metal ion and the hydroxide ion. These ones are called the alkaline earth metals. Again, if we have them in solution, they are going to form strong bases. Okay, it's these ones over here. And there's a reminder of what you would have learned about pH in Phys Sci, with some commonly encountered kinds of things. So oranges and lemons and vinegar, etc., as acids, and your drain cleaners and your laundry detergents as bases. But we didn't really do much beyond a bit of an educated guess as to what values they might be. And that's about to change. Alright, so the last lie that I'm going to tell you the truth this time about this part. But there are other lies that I've told you this year, that if you go on and study chemistry, then you'll find out the truth about them. It's probably, lie is a harsh term, it's probably more like just a simplification, rather than, like everything can be quite complex. And that is that every time I've written H+, it's a lie. Okay, because if you think about it, this is a proton. How likely is it for a proton to be hanging around by itself? Unlikely. It's pretty low, unlikely. It's very, very unlikely. And how many times do you reckon we've drawn that on the board? Quite a lot. What we actually have is this, which is called the hydronium ion. So the hydrogen ion, the proton, is just going to attach itself to the polar end of the water molecule, the oxygen part. Okay, so if we think about what does water normally look like, we've drawn it like this. So if water is slightly negative at that end, Makes sense if you're just a little proton that you're going to go and stick yourself on here, aren't you? And so in actual fact, we can't tell which one of those is if you like, a dodgy bond. And so what we end up with is that where we would say that one of those there's a positive charge on our hydronium ion. And there's a cute looking little picture of it in your booklets here. Sort of, I don't know, looks like a small head and like a teddy bear or something. Okay, so now that we have the hydronium ion, we can look at what happens in water. We have some water molecules that will dissociate. Okay. Now, very, very few. So if I changed my arrows to give you a better indication, that would be as small as I could make it, and that would be as big as I could make it. But if we think of this as a reaction, like we've done before, we can work out K, the constant for water. So now we have a subscript W, because we're looking at the dissociation constant, or the reaction, if you like, constant for water. And it's going to equal the concentrations of our products divided by the concentration of our reactant, isn't it? Now, water is our solvent here. And I think good. The way it's written here. What we have then is a very, very low dissociation of our ions. This is at 25 degrees C. And the value for K for water is on your formula sheets to remind you that it's -14. And hopefully you can start to see why look, and it's written in both ways on the formula sheet as well. Either as the hydronium ion or just as the hydrogen ion. Now, if we have pure water, that means that these are balanced, same number present in our sample of water. This would be then 10 to the -7, and this would be 10 to the -7, wouldn't it? Because our index laws would tell us that if we multiply them together, multiply these numbers, we're just going to add the indices. Yeah, does that make sense? And because we're interested in pH, which is, if you like, how much hydrogen ions, the quantity of hydrogen ions that are present. This is why, for pure water, or where our acid and base are balanced, it gives us then a pH of 7. And we'll look a little bit more on the next page into how it works there. But this is also the reason why our maximum pH is 14. So if we turn the page, for acidic substances, so solutions, then we need to have a concentration of hydrogen ions present that's greater than the number present in pure water. Okay, we have to have an excess of hydrogen ions. And the same if we have a basic solution, we would need to have an excess of hydroxide ions beyond what are present in pure water. Now, there's this quick intro to logs business, and I'm not quite sure why there's a little bit of sort of windings there that's not very helpful. The thing to remember with determining the log, for our log, we are using logs, which is log to base 10. We're not using the natural log. And so, if you find the log of 100, the answer will be 2, because it wants to know how many zeros you've got. Okay? So log of 100 is equal to 2. Log to base 10 of 100, is 2. So you can have a go with your calculators just to sort of remind yourself of how to use logs. And the same then with our example in here, that log of 1,000, so it's log to base 10 of 1,000, gives us a value of 3. And you can end up with negative numbers if our number is very small. So log to base 10 of 0.001 would then be negative 3. Okay, so just see if you can get your calculators working correctly, and especially those of you who aren't doing maths history. Yeah, that's Windows. And so the pH then, to get that as a number like we're used to seeing, pH of 6 or 4 or whatever, it's the negative log of the concentration of the acid. So this is on your formula sheets, and I'm pretty sure this is as well, so that this is also telling us that the concentration of the acid is then equal to 10 to the power of the negative pH, depending on which way you're going. So you might need to calculate the pH, depending on where the way the information is being presented. So yeah, there's a few more unhelpful indents on the bottom of that page.